Hi there, this is Miss Barber. Retailers and manufacturers need to know how a small change in price will affect the demand for a product. In this lesson, we will learn about price elasticity of demand, in which we will use calculus to predict how price change will affect demand and hence the revenue. If a small increase in price results in no change in demand, the price increase makes good business sense. However, if that small increase in price results in a drop in demand, the increase is not wise. We begin with the relative rate of change. Example 2.5.1. You received $2,000 to invest for the next year and were considering two stocks. Your analysis shows that stock A is expected to increase by $10 per share next year, while stock B is expected to increase by $50 per share next year. Which is a better deal? Actually, we don't have enough information to make a decision here. For instance, let's look at stock A. And let's suppose that stock A, so we're going to say suppose that stock A is $100 per share. At $100 per share and $2,000 to invest, you can purchase a total of 20 shares. Now, if you have 20 shares and you get a $10 per share increase in value, you would have a net gain of, 10 times 20 or $200. Now let's suppose that stock B, okay, and so we'll suppose that the price is $2,000 per share. Well, with the amount that you have, you can only buy one share. And that share is projecting a $50 per share increase. So you would have a gain of $50. The question is, which is a better deal? Well, that depends entirely upon the price per share. What matters here is the relative rate of change. Relative rate of change is defined as the derivative of the function divided by the function, which is also the derivative of the natural log function of f of x. This value is the rate of change divided by the current value. Example 2.5.2. You received $2,000 to invest for the next year and were considering two stocks. Your analysis shows that stock A is expected to increase by $10 per share next year and costs $200 per share. Stock B is expected to increase by $50 per share next year and costs $500 per share. Which is a better deal? The better deal is determined by the relative rate of change, and the relative rate of change is defined as the value of the rate of change divided by the current value. So let's consider the relative rate of change we denote with RROC of stock A. The rate of change is $10 divided by the current value, which is $200. That, when computed, is 0.05 or a 5% increase. Now let's determine the relative rate of change of B. For the relative rate of change of B, the rate of change is going to be $50 divided by the current value, which is $500. Computed, this is 0.01 or 10%. Interestingly, in this analysis, the amount of money invested does not matter in determining the best outcome. Let's observe $2,000 was invested for both stock A and stock B had a higher return. Definition: the relative rate of change of a function f of x is f prime of x divided by f of x, which is d dx, that's the derivative with respect to x of the natural log of f of x. Example 2.5.3. Find the relative change of y equals 100x squared minus 5x. To find the relative rate of change, we denote with RROC. That is equal to the derivative of the function divided by the function. So in proceeding, the derivative of y turns out to be, we bring the 2 down and multiply it to the 100, which would be 200x minus the derivative of 5 times x is just 5. We divide that by the given function, which would be 100x squared minus 5x. To simplify, let's factor out a 5 from the numerator. So factoring out the 5, that means divide. So 200 divided by 5 would be 40x minus 5 divided by 5 is 1. Divided by, factoring out a 5 in the denominator, 100 divided by 5 would be 20, and that leaves x squared, minus 5x divided by 5 leaves x. The 5's cancel, and the simplified relative rate of change, which we denote with RROC, is 40x minus 1 in the numerator, divided by 20x squared minus x. Example 2.5.4. Find the relative rate of change if f of x equals x minus the natural log of 5x. To find the relative rate of change, RROC, that is the derivative of the function divided by the function. The derivative of, so f of x equals x minus ln of x, the derivative of x is just 1, minus the derivative of the natural log of 5x would be 1 over 5x times the derivative of the inside function, that is the derivative of 5x, so times 5, divided by the function itself, x minus the natural log of 5x. We'll clean up the numerator, and we'll get 1 minus 1 over x, the 5 in the numerator and the 5 in the minor denominator cancel, times x minus the natural log of 5x. We need to simplify this, so we'll multiply the big numerator with x and the big denominator with x. That's a factor of 1. And distributing, you would get x minus 1 over x times x is just 1, and in the denominator, distributing the x, you would get x squared minus the natural log of 5x. So, RROC, the relative rate of change of f of x equals x minus ln of 5x is equal to x minus 1 in the numerator divided by the quantity x squared minus the natural log of 5x. Example 2.5.5. Determine where the relative rate of change of the function f of x equals e to the power of 2x minus e to the x plus 1 is equal to 1. So we have two things to consider. What we need to do first is to find the relative rate of change, RROC, set it equal to 1, and then solve for x. Let's begin. The relative rate of change is the derivative of the function divided by the function. So the denominator will remain the function e to the 2x minus e to the x plus 1. Let's take the derivative of the numerator. The derivative of e to the 2x is e to the 2x times 2 minus the derivative of e to the x remains e to the x, and the derivative of the constant 1 is 0. Now we will take the 2e to the 2x minus e to the x divided by the function e to the 2x minus e to the x plus 1, set it equal to 1, and this becomes an algebra problem. Let's multiply through the denominator, and so this equation becomes e to the 2x minus e to the x is equal to 1 times e to the 2x minus e to the x plus 1. Let's proceed to solve. The e to the x's cancel, and so we now have 2 e to the 2x equals e to the 2x plus 1. Let's subtract e to the 2x from both sides, and we get e to the 2x equals 1. Now we will use properties of logs. Taking the natural log of both sides, you will get, so let's just go ahead and practice ln of e to the 2x is equal to ln of 1. Property tells us that ln of e to the power of anything is whatever that power is. The natural log of 1 is 0. And so when you solve for x, divide by 2 on both sides, and the value we get for x is 0. Example 2.5.6, find d dx, that is the derivative with respect to x, of the natural log of f of x using the chain rule. So we'll do d dx of the natural log of f of x. The rule tells us the derivative of the natural log of x is 1 over whatever the function is times the derivative of the inside function, which we denote with f prime of x, and that gives us f prime of x, which is the derivative of f of x, divided by f of x. Let's observe that this expression gives you the relative rate of change. Definition. The percentage rate of change is the quantity 100 times the derivative f prime of x divided by f of x with the percentage notation annexed. Example 2.5.7. Find the percentage rate of change of f of x equals 150 plus 30x when x equals 2. The procedure here is we first find the relative rate of change RROC function, which we know is the derivative of the function divided by the function. So let's compute. The derivative of 150 is 0. The derivative of 30x leaves 30. We divide by the function 150 plus 30x. Now we compute the relative rate of change, RROC, at x equals 2. That means you put in a 2 every place there is an x. So we have 30 divided by 150 plus 30 times 2. This is 30 divided by 150 plus 30 times 2, which is 60, is 210, and that reduces to 1/7. Decimal approximation would be 0.1428 ... And to express this as a percentage, we move the decimal point to the right 2 spaces and write it as 14.28%.